that it is of class C2. So here are data. I assume that 0 is less than or equal to H. H is of class C2 of RD, is even, strictly convex, and limit when s goes to infinity, h of x over s to the power p equal to infinity for some p between 1 and infinity. And we saw that this condition implies that the gradient h is from RD to RD is a bijection. So now I am going to assume that mu naught, mu 1 are random measures, so they are Borel regular probability measure. On RD. And my notation start with first C of xy is h of x minus y. This is the cost to transport a unit mass from S to Y. The Monge cost, the Kantorovich cost, m of gamma, is the integral over RD cross RD, C xy, gamma dx dy. And the Monge cost of a map T is the integral over RD of C of x, T of x, mu naught dx. And gamma, mu naught, mu 1. This is a set of gamma Borel regular probability measure on RD cross RD, such that the first marginal of gamma is mu naught, the second marginal of gamma is mu 1, and pi 1 of xy is x, pi 2 of xy is y. Eventually, J of UV, UC, is the set of UV such that UV is from RD to negative infinity, infinity, are upper semi-continuous, and U of x plus V of y is less than C of x, y for every x, y in RD. And U restricted to, U is not identically negative infinity, V is not identical, V is not identically negative infinity. So to avoid triviality, we are going to assume that the infimum of C over gamma is not plus infinity, because if it is plus infinity, everything is a minimizer. A sufficient condition for C not to be identically infinity is we are going to assume that the integral over RD cross RD C of mu naught mu 1 is less than infinity. Or we can replace that by a stronger assumption, or there exists gamma bar, which has mu naught mu 1 as marginal, such that C of gamma bar is less than infinity. So there I took gamma bar equal to mu naught cross mu 1. So the next result I am going to state, let me make an analogy with something you are familiar with, because I want to insist on a question asked by Hermano. Assume you are on a matrix, in a matrix space, and you take a curve in that matrix space. Okay, so by definition, this curve to be a geodesic means it satisfies a certain ODE. Right? So for instance, let me give you an example. Take L of xv is the sum of gij of x, vi, vj. Take this Lagrangian. And consider a curve such that d over dt, gradient v of L of x, s dot, equal to gradient x, L of x, s dot. Right? This is called a geodesic. Okay, I am not saying minimal geodesic. It is called a geodesic. It satisfies that ODE. One can show that if you take any 2 points, so this is my curve x. Then I choose any arbitrary 2 points on my curve. I assume that my curve satisfies this condition. And I consider any other curve passing through these 2 points. This white curve will have the smallest action if these 2 points are not far from each other. So my statement is, once you satisfy this ODE, if I define the action A of x to be the integral from t0 to t1 L of s of t, s dot of t, dt, and assume that t0 minus t1 is small. So it is a constant which depends only on L. Then whenever this equation is satisfied, if I choose 2 points on the curve, any other curve passing through these 2 points will have a larger action. And so this property characterizes the minimizer of this action. Once I fix the 2 points, once I fit any arbitrary 2 points. the result I am going to state is the analogous result of that. My ODE, the analog of my ODE is I take gamma. I look at the support of gamma. I impose a geometric condition is on it. It is C cyclically monotone. So compare this condition, this geometric condition, to that geometric condition on a curve. Then the statement is, if I take any over gamma bar such that it has the same marginals with gamma, then the cost of gamma bar is bigger than the cost of gamma. So you see that the geometric characterization here is given by a C, as the geometric characterization here is given by my L. And so this result is the analog of what we well known in Riemannian geometry. So let me start with the definition of C cyclically monotone. So let S be a subset of RD, cross RD, be a non-empty set. We say that, so I am adding that so that I don't have to repeat it, and the empty set is not very useful. We say that S is C cyclically monotone if for every n integer, every sigma permutation of n letters and every Si, Yi, I from 1 to n subset of S, we have that the sum I from 1 to n, CSI, Yi, is less than the sum I from 1 to n, CSI, Y, sigma I. So without loss of generality, it is not a loss of generality to take sigma I plus 1 equal to sigma I equal to I plus 1 with the convention that n plus 1 is identified to 0. Let me, n plus 1 is identified to 1. Okay, so what I mean is sigma of 1 equal to 2 up to sigma of n minus 1 is n, and sigma of n is 1. So it is not a loss of generality to take that sigma, because I can always change the order of my points. So the plan is to show that the support of every optimal gamma is cyclically monotone. Then to show that the support is set C cyclically monotone, imply S is in the subdifferential, the C subdifferential of a function U. More precisely, I will have that U of X plus V of UC of Y equal to C of XY. for every xy in S. Okay, so this is what that means. As a consequence, when I integrate the left-hand side, I have j of u, uc. The right-hand over gamma, the right-hand side, I have the cos. And so I conclude the duality result. So this is the plan I want to complete today.
Not understand this definition. This S content B-I-S, so it's contained in the Cartesian product, right?
Yes.
So that, yeah, then it makes sense because so it's disposed in the Cartesian problem in such a way that any other reordering of changing the coordinate will give something that is less than.
We give a higher cos.
Yeah.
Yes. So I want to show this, that. I am going to start with, I am going to approximate mu naught and mu 1 by measure of compact support. And in that case, it will be easy to show that the support of gamma n are c-cyclically monotone. Then I'm going to show that gamma is a limit of gamma n. And one of the homework problem in homework problem number 1, you were asked to show that if the support of a sequence of measure gamma n is c-cyclically monotone, you were asked to show that if z belongs to the support of gamma n, if gamma n converge with star to gamma, this implies that z is a limit of Zn. Zn is in the support of gamma n. So once you have this implication, it means that it implies that if the support of gamma n is c-cyclically monotone, the support of gamma is also cyclically monotone. And so you have this first implication. From here to there, I am going to have a representation formula for you. I am going to have an explicit representation formula for you. Reminder. Assume for a moment that mu naught, mu 1 absolutely continue with respect to Lebesgue measure. The support of mu naught, the support of mu 1 are contained in a ball of radius R. We show that existence of U B bar R into R Lipschitz and T from RD to RD Borel such that if you apply the cos, the Monge cos to T, you get J of U, UC. And T pushes mu naught forward to mu 1. C of X y equal to u of x plus uc of y if y equal to t of x. Okay, so another way of writing that is given x in the domain of u, there exists t of x is a unique y such that u of x plus uc of y is a c of x, y. Furthermore, t is continuous on the domain of the gradient of u. Okay. So when the support of mu naught and mu1 are bounded, then the optimal map exists. It is unique, and it is characterized by this property. Define set gamma t to be identity cross t, push forward mu naught. In other words, what I am saying is gamma t of a set B. This is mu naught of a set of x in Rd, such that x, t of x, is in B. Okay, and we check that gamma t has mu naught and mu1 as its marginal, because if I take B equal to A cross Rd, gamma t of A cross Rd is mu naught of A. And if you take gamma t of Rd cross A, and you use the fact that t pushes mu naught forward to mu1, you get that it is mu1 of A. Yeah.
The concept of cyclic monotone, if the support is the whole Rd times Rd, then you get an equality there, right?
The support can never be the whole
Can never be.
Rd cross Rd.
But why not?
Oh,
Based on your assumptions, or?
Because Rd cross Rd cannot be C cyclically monotone.
Okay.
Right? You will be saying that if I take any sequence Si in Rd cross Rd, I permute them, I have a higher cost, which is a contradiction.
Right.
Because I can start with a permute sequence, and that will not be possible. And in fact, this is suggesting that if a set is a C cyclically monotone, it is D minus 1 rectifiable. Right? Because it will have to satisfy this condition, U of S plus UC of Y is C of X, Y. So for each X, I am going to look for the set of Y satisfying this equation. If I have differentiability for U, then I see that Y will be uniquely determined. So only for a set of zero measure, Y will not be uniquely determined. And so the set will be D minus 1 rectifiable, meaning it is a union of a countable union of C1 manifold plus a set of zero measure, D minus 1 zero measure. theorem. The support of gamma t is C cyclic. Let me. So assume for a moment that is a C cyclically monotone under assumption 1. So proof, set S to be the set of X in the ball dr such that the gradient of U of X exists. U is Lipschitz. U is Lipschitz, and so this set is a set of full measure, meaning the complement on that set in the ball is a set of zero measure. So since U is Lipschitz, the Lebesgue measure of the ball minus S is a set of zero measure, which implies that mu naught of the ball minus S is a set of zero measure. So last time we checked that this set is measurable. So the way to check it is the partial derivative of U, the set where the partial derivative of U with respect to S1 is the set where that partial derivative exists is measurable because of the following reason. You are saying that the left derivative equal to the right derivative. The left derivative is a Borel function. The right derivative is a Borel function. Therefore, the set where two Borel functions agree is measurable. And so the set where derivative of U with respect to Si is measurable for each I. Therefore, the set where the gradient exists is measurable. So this is something we checked last time. However, if I take directly the support of that set, I will have some technical difficulty, which you will see soon. Let me start with the first claim. Claim S is C cyclically monotone. So proof of the claim, let sigma from n to 1n be a variation and let Si, yi, I from 1 to infinity be a subset of S. So on S, the gradient of U exists. But when the gradient of U exists, xy in S implies that y is uniquely determined and is T of x. We have C of xi, yi is u of xi plus uc of yi for I from 1 to n. No, sorry. I want to say that claim 1. If I define this to be identity cross T of S, this is C, cyclically monotone, because I want a subset of RD cross RD. So by definition, being here mean yi is T of Si. But T of Si is characterized by the fact that U of Si plus Uc of yi is C Si yi. And we have a C of xi, y sigma I, is greater than or equal to U of xi plus Uc of y sigma I. Okay? Because by definition, Uc of y is the infimum of C of xy minus U of x, which implies that Uc of y plus U of x is less than C of xy for every sy. So I use that property to conclude this. Thus, the sum I from 1 to n, C of xi, yi, call this 2 and call that 3. This is the sum I from 1 to n, U of xi plus Uc of yi. If I use 2, I can replace the C of SIYI by U of SI plus UC of YI. But observe that this is also the sum I from 1 to n of U of SI plus UC of Y sigma I. Because sigma is a bijection. But if I use 3, this is less than the sum I from 1 to n, C of SI, Y sigma I. And so I am done. Second, since S is Lebesgue measurable, so I will just write measurable, S can be written N union from 1 to K from 1 to infinity of KK, where N is a set of measure 0, Kk is compact, and kk is a subset of k plus 1. So S is a measurable set. I can write that S is a sup over the compact set K, subset of S, of LD of K. Take a maximizing sequence, KK. Replacing KK by K1 union K2 up to KK, I can assume without loss of generality that my sequence is increasing. Define N to be S minus the union of KK. This is a set of 0 measure, and I have the quality I wrote there. T is a Borel map. The image of T, if you apply T to a Borel set, you don't know that you have a Borel set. If you apply T to a measurable function, you don't know that you have a measurable function or a Borel set. You don't know that you have a Borel set or a measurable set. However, since T is continuous on S, the image of a compact subset of S will be a compact set. And so a compact set will be a Borel set. Since T is continuous on S, so if you don't remember how we proved that, let me recall briefly why T is continuous. I take a sequence Sn going to S, T of Sn going to Y. And I want to know if Y is T of X. The relation between Sn and T of Sn is C of Sn, T Sn is U of Sn plus UC of T Sn. U is Lipschitz. When I pass to the limit, I let n go to infinity here, I get a C of X, Y. This one goes to U of X. UC is upper semi-continuous. Therefore, I get this inequality, UC of Y. But UC is bigger than, C is bigger than U plus UC. Therefore, this inequality implies that C of XY is U of X plus UC of Y. But when X is in the domain of definition of U, Y is such that the quality hold is uniquely determined, and Y is T of X. So this proves that T of Sn converges to T of S, which means that T is continuous. So since T is continuous, identity cross T applied to Kn is a compact set. And so it is a Borel set. Hence, if I write gamma T of identity, let me call this K calligraphic N, K calligraphic N. This is mu 0 of Kn. So I replace B by K calligraphic n. So gamma t of k calligraphic n, this is mu0 of the set of x, such that s, t of s, is in k calligraphic n. But this is the set of x such that s is in kn. And so that is mu0 of kn. Kn is a subset of S. Therefore, I have this inequality. This goes to 1. Hence, gamma t of S must be 1. So this goes to 1, imply gamma t of S is greater than or equal to 1. But gamma t of RD is a measurable set. If I write gamma t of RD, this is mu naught of RD. Mu naught of RD is 1. Gamma t is a subset. S is a subset of RD cross RD. Therefore, gamma t of S is 1. We conclude that. We conclude that gamma t of the closure of S is 1, because the closure of S is a set which is bigger than S. The support of gamma t is the smallest compact set which take measure 1. So if you take any closed set which has measure 1, it contains the support of gamma t. S bar is a closed set of measure 1. Therefore, S bar contains the support of gamma t. Hence, the support of gamma t is contained in S bar. Since S is C cyclically monotone, so is S bar, and so the support of gamma t is C cyclically monotone. So if I take a C cyclically monotone set, any subset of that will be C cyclically monotone, and this proves the theorem. Any question? So here is what I want to do next. Assume that we are given a function u from Rd into negative infinity plus infinity. And I want to compute uc of x, which is by definition the infimum over y, c of xy minus u of x. Assume that given x bar, I have an infimum y bar. or assume that given x, I have y, which is a minimizer. So that will mean that C of x, fix x in RD. Assume y is a minimizer. Then this will mean that C of xy minus U of x is smaller than C of S prime y minus U of S prime for every S prime. So if given x, I can find a minimizer y, then this property will be satisfied for every x prime. The next theorem I want to state will say that if I have a set S calligraphic, which is C cyclically monotone, anytime I take xy in that set, then they minimize the functional. Then y minimize this functional, which means this inequality holds. Let S, a subset of RD cross RD, be a C cyclically monotone set. Then, first, there exists U from RD to negative infinity plus infinity, such that U is not identically negative infinity, and for every x, y in S, C of xy minus U of S is less than C of S prime y minus U of S prime for every S prime in RD. So I am constructing a function U such that whenever I take x, y in calligraphic x, this functional achieves its minimizer at this function achieves its minimizer at x. Second, if x, y belong to S, then U of x, U C of y are finite. They are not plus infinity, minus infinity. And U of x plus U C of y is C of x, y. Last condition, U, UC are upper semi-continuous. What is trivial is that UC is upper semi-continuous, and what will require a little bit of work is to prove that UC. It's proved that U is upper semi-continuous. UC is an infimum of upper semi-continuous function, and so it is upper semi-continuous. So once I have, by definition, U plus UC is less than C. Once I have that U and UC are upper semi-continuous, once I know that UC and U are not identically plus infinity, I can conclude that UC is in my set calligraphic U subscript C. So this is our goal, and the rest will be a direct consequence of that goal. Proof. This proof is due to Rockefeller in the case where C of x, y is x minus y squared. My set is C cyclically monotone, and so I assume it is non-empty. This is part of the definition of C cyclically monotone. Let S naught, Y naught be in S. Define U of S.
In the case where C is exactly this one, you said the modulus of x minus y squared, this one of Rockefeller.
Yes.
Is there any geometric meaning for being C cyclically monotone?
Yes, it means that I am going to change my function U and define psi of x to be s squared over 2 minus U of x. So if C of xy is 1/2 x minus y squared, I define that function. So C cyclically monotone means that psi is convex, and the S will be the subdifferential of psi.
Which U is this? Is it in the definition of cyclically?
Okay. So here I am stating the theorem. If S is a C cyclically monotone, there exists U such that some property holds. But actually, I can also state the property that if there exists U which satisfies this property, then the set of xy is a C cyclically monotone. So there is a one-to-one correspondence between the set of S and the set of U. Okay. I want to characterize the set of S, which is equivalent to characterizing the set of U. So whenever you give me a U, I am going to define psi this way. And I am saying U, S C cyclically monotone is equivalent to psi is convex. And I choose S to be the subdifferential of psi. So the geometric property is on the graph, not on the graph of U, but on the graph of psi. And the graph of psi will be S if U was smooth. If U is not smooth, it will be the subdifferential of psi.
You mean like the domain times this differential?
So assume U is smooth to make things simple. The subdifferential is the set of x gradient psi of x such that S is in RD. So if I want to draw a picture, the set S will be the graph of my converse function. I am going to define U of S to be the infimum over P greater than or equal to 1 integer, the infimum over Si, Yi, I from 1 to P, subset of S. And then I am going to compute something. I have C of S naught, Y naught, plus C of SP, YP. And here I am going to increase the cos. I will have C of S1, Y naught, plus C of SP, YP minus 1, plus C of X, YP. So let me explain what I am doing, what I wrote there. C of X naught, Y naught, plus C of SP, YP is smaller than or equal to C of S1, Y naught, plus C of SP, YP minus 1, plus C of X naught, YP. Okay. The set is cyclically monotone. So if you change the order, you increase the total cost. I am changing, this is the element of the set. I am changing the order. So I am going to replace S naught by S1. I am rewriting the same thing exactly, plus C of XP, YP. Okay, so here you see that I replace S naught by S1 up to SP minus 1 by SP. And then I am going to replace SP by S naught. I have increased the cost. Now see what I have done here is I have removed this and replace it by S, YP. So if I replace that by S, YP, I need to save S naught, YP, and subtract S, YP. So originally, this is what I have. I have S naught YP. And I am writing that S naught YP is CS YP minus CS YP. So I write this and I subtract it. And I am rewriting CS naught YP. Okay, again, I have done nothing but this. CS naught YP is CS naught YP minus CX YP plus CX YP. So this is the infimum over p greater than 1, the infimum over xi, yi, I from 0 to p, subset of S. And I am going to write C x naught yp plus C sp yp minus 1 plus C s1 y naught minus C s naught y naught plus C sp yp. And I need to add C s yp minus C s naught y naught yp. Okay, so I have replaced Cx yp by C s naught y naught minus C s naught, so by C s naught yp minus C s naught yp plus C x yp. The fact that S is cyclically monotone says that this is bigger than that. So that is bigger than the infimum over P greater than 1. The infimum over Si, Yi, I from 0 to P, C x Yp minus C S naught Yp. So in particular, observe that if S equal to S naught, if I plug S by S naught here, this is 0. Call this 4. 4 implies that U of S naught is greater than or equal to 0. Take a P equal to 1, x1 equal to S naught, y1 equal to y naught, and plug that there to discover that U of S naught is less than or equal to 0. So U of X is less than this expression for every P and every sequence. In particular, if I take a P equal to 1 and I take a S naught Y naught, S1 Y1 with a S1 Y naught 1 equal to S naught Y naught, if I plug this here, I will get a value which is bigger than or equal to U of S naught. And this giver U of S naught is less than or equal to 0. Hence, U of S naught equal to 0. And we get the first part we want. We get that U is not identically negative infinity. So call this I. Now fix X, Y in S. I want to show this inequality. I don't know, probably this minimization problem doesn't have a minimum, but I can take a minimizing sequence. So for each epsilon positive, choose P greater than or equal to 1, and Si, Yi, I from 0 to P, subset of X, such that U of X is bigger than negative epsilon plus C of X, Yp, plus C of X, P, Yp minus 1, plus C of X, 1, Y naught, minus C of Sp, Yp, plus C of Sp minus 1, Yp minus 1, plus C of X naught, Y naught. Okay. So my functional is defined as an infimum over a certain set. I can take a minimizing sequence in that set. And I'll have data U is close to this value up to an error epsilon. Now, Sy belong to S calligraphic. Therefore, I can set Sp plus 1 to be X, Yp plus 1 to be Y. And so I have data Sp plus 1, Yp plus 1 belong to S calligraphic. Call this 6. By 6, which one? This?
Why 6? You can call it as you wish, but that's not possible.
Yes, because I forgot if I had 5. Yes, I can call it 5. So let me rewrite 5. U of X is bigger than negative epsilon plus, I will start with this. This is C. This is a CSP plus 1 YP, because I have set X to be SP plus 1. And I am going to add a CSP YP minus 1 plus CS1 Y naught. And now I am going to add something which I want to subtract, CS prime YP plus 1. And I need to subtract what I added, CS prime YP plus 1. By 5, if S prime is an arbitrary element of RD, I can write the first part. I can write this first part as what is there, as this. Now, in my parenthesis is C of SP YP plus C of S naught, Y naught, with a negative sign. I am going to add C SP plus 1, YP plus 1. And since I subtracted that, I will have to add it. C SP plus 1, YP plus 1. But this is CXY. Now, you look at the definition of U of S prime. It is the infimum of such an expression where P is arbitrary. Therefore, if I take P plus 1, I have something which is bigger than U of S prime. So this is bigger than equal to negative epsilon plus U of S prime plus C of X, Y, minus C prime of X, Y. YP plus 1 is Y. Now you compare that with what I want to prove. You see that it is what I want to prove with an epsilon in it. But epsilon is arbitrary. I can let epsilon go to 0. Since epsilon is arbitrary, we obtain I. Okay. Now I can read from here that if I minimize this over S prime, the minimum is attained at X. By I, if XY is in S, then U of X, then the infimum over S prime of C of S prime Y minus U of S prime equal to C of X, Y, minus U of X. And this, by definition, is UC of Y. Let SY be in S. So what I want to do, let me rewrite this as I can move U of S prime here. And remove it from here. And I can move U of S there and remove it from here. And now I can move C here minus C of XY. Set S naught, S prime, equal to S naught in I. Then U of S naught is 0. 0 is less than C of S naught. y plus u of x minus c of x, y. So this is telling me that u of s cannot be negative infinity. Because it is telling me that u of s is bigger than c of xy minus c of s naught y. It is telling me that I have this. And so u of s cannot be negative infinity. Hence, if xy belong to S, u of x is not negative infinity. And clearly, u of s is an infimum. It cannot be plus infinity. The set on which I am minimizing is non-empty. So I just take anything here. It is going to give an upper bound. And so, under this condition, u of s is between negative infinity and plus infinity if I know that xy belong to calligraph S. But from here, if I call this 6, this together with 6 imply that uc of y is between plus infinity and negative infinity. So this proves that u and uc are not identically negative infinity. And this equality holds on S. So that is an important fact which we are going to use. So if you look at my function here, it depends on x here and nowhere else. Therefore, it is a continuous function of x, which means it is upper lower continuous as a function of s, what I am minimizing. If you minimize upper lower semi-continuous function, you get an upper lower semi-continuous function, and so u is upper semi-continuous. By definition, uc is an infimum of upper semi-continuous function. Therefore, uc is upper semi-continuous. Since uc are infimum of upper semi-continuous function, they are upper semi-continuous. Thus, we reach the conclusion uc belong to U calligraphic C. So let me summarize what I done here. Rockefeller proved that if you have a subset of RD cross RD, which is cyclically monotone, he calls it, the C cyclically monotone is a generalization of that. If it is cyclically monotone, meaning that when you take the cost function s minus y squared, which is equivalent to s minus y squared over 2, when you take any sequence of points, this arrangement gives you the minimal cost. If your set satisfies that geometric condition, then it is a subset of the subdifferential of a converse function. And you can see the definition of subdifferential is u of s prime is less than u of x plus minus c of xy minus c plus c of s prime y for every s prime. I would say that xy is in the subdifferential, the c subdifferential of u if this property is satisfied. Theorem? So recall that at the beginning of the lecture, I started with mu naught, mu1 probability measure arbitrary. Okay. So let mu naught n, mu1 n, be Borel regular probability measure. Such that the support of mu naught n and the support of mu 1n are in the ball of center 0 radius n. Mu naught n, mu 1n are absolutely continuous with respect to Lebesgue measure. And we have the following convergence. The limit when n tends to infinity, the integral over Rd of phi, mu naught dx is the integral over Rd of phi d mu naught. The integral over Rd of phi d mu 1n is the integral over Rd of phi d mu 1. This for every phi which is bounded and uniformly continuous. Okay. So we saw that given mu naught, a probability, Borel probability measure, you can approximate it by such a subsequence. And so making this assumption is reasonable. It is not something empty. Let Tn be the unique optimal map which pushes mu naught n forward to mu 1n. We know that such an optimal map exists, and set gamma recall that gamma T of B is and set gamma Tn to be identity cross mu n push forward mu naught n. This is the optimal gamma in Kantorovich problem. Up to a subsequence, gamma Tn converges with star to some gamma which has mu naught U1 as a marginal. Still, we know that. But the only thing I need to add is we have that. The support of gamma is a C, cyclically monotone. So that is the only new small thing I am adding. And the proof. Since gamma Tn converges with star to gamma, given x, y in the support of gamma, there exists Sn, Yn in the support of gamma Tn such that xy is the limit over n of Sn Yn. Okay, so this is homework assignment number 1. Since the support of gamma Tn is C, cyclically monotone, we conclude that the support of gamma is C, cyclically monotone. So corollary, let gamma be as above. There exists U from Rd into negative infinity, such that U of x plus UC of y equal to C of xy for every xy in the support of gamma. U of x, UC of y are real number for every xy in the support of gamma. UC isn't UC. So this is a consequence of the theorem before this and the fact that the support of gamma is C-cyclically monotone. Call this corollary 1, corollary 2. We have SOP over UC of J equal to N over gamma mu naught mu 1 of the Monge cos, and this is C of gamma, and that is J of UC. So the proof of that, we know that the SOP over UC of J is less than the nth over gamma having mu naught and mu 1 as marginals of the Monge cos. It suffices to show that J of UC is the cos of gamma. So I have two graphs. One is above the other. If they intersect at one point, then the graph which is above has a minimum there, and the graph which is below has a maximum there. But set N to be the set of xy such that U of S plus UC of y. Set S to be RD cross RD minus the support of gamma. This is a set of zero measure. Then if I write the integral over RD cross RD of U of X plus V of Y, gamma dx dy, this is the integral over N of U of X plus V of Y, gamma dx dy, plus the integral over the support of gamma, U of X plus V of Y, gamma dx dy. And that is J of UC. So by V, I mean UC, and UC. N is a set of zero measure. Therefore, this integral is 0. On the support of gamma, this is C of x, y, gamma dx dy. But that is the integral over RD if I integrate on the support of gamma, or on the support of gamma union, the complement of the support of gamma have the same thing. And so I have this inequality, which conclude. So this is the fundamental result of the mass transport theory in the full generality, without any restriction on the support of mu0, the support of mu1, on the fact that they are absolutely continuous. So I want to show more. I want to show that there exists. We prove existence of an optimal map for a Monge problem when the support of mu0 and the support of mu1 were compact. And I want to remove that condition. So when the support of mu0 and the support of mu1 were compact, we show that U is Lipschitz. When the supports are not compact, there is no hope that U is Lipschitz. And in fact, you can construct counterexample where U is not Lipschitz. This is why I have assumed that H is C2, and I'm going to prove that using the fact that H is C2, and has the second derivative has an upper bound, then you get immediately that U is convex up to a linear function. And so convexity gives you local Lipschitzness. So theorem. Since the second derivative of H is less than lambda identity, if V is from RD to negative infinity, then NU is VC, then the function x goes to lambda s squared over 2 minus u of x is convex. So in particular, if c of xy is x minus y squared over 2, then the second derivative is exactly the identity, and we have this property. The theorem I am stating is true without that extra assumption, but it requires bigger machinery to reach this conclusion. If you make this assumption, then you get the conclusion very easily, as you will see soon. Proof. Set Ly of x to be lambda s squared over 2 minus h of xy minus y. Okay. So maybe not to be very mysterious, let me recall that. U of x is the infimum hxy minus v of y. Y is in Rd. Okay? Which means minus u of x is the supremum of that. Therefore, lambda s squared over 2 minus u of x is the supremum over y in Rd of lambda s squared over 2 minus h of x minus y plus v of y. And call this L y of x. The supremum of convex function is convex. So if I can show that for each y Ly of x is convex, I am done. For smooth function, convexity is equivalent to the second derivative are non-negative. So, but the second derivative with respect to x, Ly of x, is lambda identity minus the second derivative of h at sy, and this is non-negative. This proves that Ly is convex, and so lambda s squared over 2 minus u of x is convex as a supremum of convex function. So convex functions are locally Lipschitz, and so they are differentiable almost everywhere. So let me check formally that convex functions are locally Lipschitz. So let me check that the gradient is bounded on bounded set. So fix x not in Rd or in the ball of radius r. I want to show that the gradient of f, of a convex function f, assume f from Rd to r is convex, which implies f is continuous. The fact that it doesn't take infinite value implies that it is continuous. Then I have that the gradient of f at s naught, if I multiply that with x minus s naught, this is below f of x. So the tangent plane at s naught is entirely below the graph of the function. This is a complete characterization of convexity. Okay. So take x naught, take s equal to s naught plus gradient of f at s naught divided by gradient of f at s naught. And plug this here. You have f of s naught. There you have a gradient of f s naught, because s minus s naught multiplied by this unit vector is the gradient of f minus s naught. This is less than f of s naught plus gradient of f s naught divided by the gradient of f at s naught. I am going to move f of s naught here. And so this is less than the supremum f of s naught plus z minus f of s naught, where s naught is less than r and z is less than 1. Since my function is continuous, then I get that the gradient is bounded uniformly on that ball. There is another beautiful result which tells you that the second derivative are bounded. And it is due to the fact that since the second derivative of f is non-negative, the following norm are equivalent. This is the sum of the eigenvalue, the absolute value of the sum. But the sum is non-negative. This is equivalent to the sum of the eigenvalue, which is equivalent to the square root of lambda 1 squared plus lambda 2 squared, and so on. So if I can show that this is bounded, I am done. But when I write the integral on the ball of Laplacian of f, this is the integral on the boundary of the gradient of f multiplied by the unit norm. But the gradient of f is bounded on every compact set. Therefore, this integral is bounded, and so the integral of the Laplacian is bounded. So what I am learning is just the fact that this function takes finite value is telling me that the integral of the second derivative is bounded. So in conclusion, U is locally Lipschitz because up to a quadratic form, U is a convex function. Theorem, and this will end. Suppose mu naught is absolutely continuous with respect to the Lebesgue measure. Then there exists a unique T that minimizes S goes to the integral over RD T bar Cx T of x mu naught dx among all the Borel map T bar that push mu naught forward to mu 1. And if I finish this proof, next lecture, I am going to change gear. I am going to go on a different direction, which is also, if you get fed up with seeing the same result, it will be another fresh direction which you can follow, even if you didn't follow this carefully. Usually, I follow the first 20%, and then I block my mind. And it is better if I start with a new topic. Let gamma be obtained as a limit of gamma Tn as above. Let U UC in UC be such that J of UC, J of UUC equal to the cos of gamma, replacing since UCC is greater than UC, U, we have J of UC, C, UC is the cos. And so replacing U by UCC if necessary, we may assume without loss of generality that U is VC, where V is UC. Okay? Because if I do VC, I get UCC. And so I have what I want. I did that because I can conclude that hence U is locally Lipschitz on its domain. And so it is differentiable almost everywhere. Recall that if xy belong to the support of gamma, u of x plus v of y equal to c of xy. I want to show that my gamma doesn't split mass. To each x, I can associate a unique y. This is equivalent to saying that T exists. But I have a following property. U of S prime plus V of Y minus C S prime Y is less than or equal to 0. Because U, V belong to U calligraph C. This means that that function attains its maximum at x. And so S prime goes to U S prime plus V of Y minus U minus C of S prime Y attain its maximum at x. If the gradient of U of x exists, then 0 will be the derivative with respect to x, U, S prime, plus V of y, minus C, S prime y. And that is at S prime equal to S. That is U of x minus the gradient h of x minus y. Hence, y equal to x minus the gradient of h inverse gradient of u of x. And so y is uniquely determined. Therefore, I cannot split mass unless I am not at a point of differentiability. Set S to be the set of x such that the gradient of u of x exists. If I write a gamma of RD minus S cross RD, this is mu naught of RD minus S. This is a set of 0 measure because with respect to Lebesgue measure, that is a set of 0 measure, but mu naught is absolutely continuous with respect to the Lebesgue measure. So that set is a set of 0 measure for gamma. Hence, if F is continuous or compact support from RD to RD, the integral over RD cross RD of f of xy gamma dx dy is the integral over x cross RD of f of xy gamma dx dy. So call this by definition T of x. When S is in S, then y is T of x. So this is the integral over RD cross RD of f of S T of S mu naught ds. Sorry, gamma dx dy. This being, the complement of this being a set of zero measure, I can write that this is the integral over Rd cross Rd of f of x, t of x, gamma, dx, dy. But gamma has mu naught and mu 1 as the marginals, so I can conclude that this is the integral over Rd of f of x, t of x, mu naught dx. Take f of x, y, to be of the form L of x to get data. The first marginal of gamma is mu naught. Take f of xy to be g of y to get data. Sorry. T pushes mu naught forward to mu 1. Maybe I better do it. Call this 7. So one may complain that here I have a f of compact support, but if this equality holds for f of compact support, it holds for every f bounded, because I can approximate every bounded function by function of compact support. By 7, the integral over Rd of g of y gamma dx dy is the integral over Rd of g d mu 1. I am using that with second marginal of gamma is mu 1. Okay. So here I use 7. This says this is the integral over Rg of g of t of x mu naught dx for every f. This is the same thing as saying that t pushes mu naught forward to mu 1. By 7, the integral over Rd cross Rd of c of x, y, gamma, dx, dy is the integral over Rd of c of x, tx, mu naught dx. This is what 7 tell me. But the left-hand side is the cos of Monge, and the right-hand side is, the left-hand side is the cos of Kantorovich, the right-hand side is the cos of Monge. This shows that you see, this shows that T is the minimizer in the cos of Monge. Now, what about uniqueness? You see that I have no choice here. If there is another T, which is a minimizer, it must satisfy this condition. But when this condition is satisfied, Y is uniquely determined. So there is a unique T and there is a unique gamma, which means that we have proven an existence of optimal map for general measure mu naught, mu 1, provided that mu naught is absolutely continuous with respect to Lebesgue measure, and I did not assume that mu 1 was absolutely continuous. If I made the assumption that mu 1 also is absolutely continuous, I can conclude that T is invertible. So this is existence of optimal map, which is one of the central results of the theory, which has generated a lot of interest for several years. So starting next week, starting next lecture, what I want to do is to show you how this can be applied to solving some equation in PDE. Okay, so I'll stop here.